So I'd like to first of all introduce Carla, who's won this year's Glossop Award. And Carla came top out of quite a large field of entries and very strong entries. So I hope you're going to enjoy this. Carla. You want to use that?
Well, thank you everyone for coming here tonight, and thank you very much for giving me the opportunity to be here today. My name is Carla Martin-Clave, and today I'll be talking about the role of engineering geology in the energy transition, and I will be putting the focus on the current climate emergency and salt caverns as a storage solution for the energy transition. Just a little bit about me. I finished my PhD in underground gas storage in salt caverns last year. And since I finished my PhD last year, I've been working at Jacobs as an engineering geologist. So, as you might know, we live in a world which is facing crisis after crisis. We've been through financial crisis in the past. We've just finished a global pandemic crisis, and we are going through global cost of living and energy crisis right now. So the future ahead looks pretty challenging, but I'm sorry to say that things are going to get even worse. So we've been hearing a lot about the climate change for a long time and global warming, and it's been in the last years we've seen how the public has been started to be as well very more concerned about this topic. So global warming, it's the long-term increase of temperatures from the Earth's surface from the pre-industrial period. And these increase in temperatures can develop in changes in the global climate with catastrophic consequences to the life in our planet. So the United Nations with the scientific communities have been working together in order to find solutions, and they decided to put the maximum increase of global temperatures to 1.5 degrees Celsius. However, in the last 2017, we already reached 1 degree Celsius of increase in global temperatures. And at the current warming rate, it's been calculated that we'll be reaching this maximum 1.5 degrees Celsius by 2040. However, we don't need to wait until 2040. To see how bad the situation can get. On the right, you can see a picture of the UK this summer, when we had a lot of droughts going through Europe and the UK, and when the UK experienced for first time in record temperatures over 40 degrees Celsius. So the house is on fire. The house is on fire, and we need to act now. We need to act to save the house and our lives. Those pictures here are the screenshots of the news we've been seeing during the whole summer. These are the wildfires linked to the heat waves we've been experiencing this summer. But although those pictures are from the UK, we can see this trend repeating all over the globe. And unfortunately, this climate crisis doesn't come only with heat waves in the summer. It comes with stronger storms, floodings, the melt of the polar ice, and as well the rise of sea levels. So what can we do? Let's save the house. As I said previously, the United Nations have been working with different governments and as well with the scientific community in order to get international agreements to prevent the most catastrophic consequences of this increase of global temperatures. And all those agreements, international and national agreements, well, they have one objective in common. And this objective is to limit the increase of global temperatures to 1.5 degrees Celsius by decreasing the emission of greenhouse gases into the atmosphere. And at this point, you might be thinking, okay, but what can we do? What can engineering geology do to help fixing this problem? So engineering geology is a very important part of the solution and the equation to find the better solution to this climate change problem. So engineering geology can provide underground storage solutions to store either hydrogen, energy storage in the form of compressed air, and as well CO2. And we can reutilize the resources, our underground resources, such as depleted gas reservoirs or aquifers, and even salt caverns. Engineering geologists are responsible of assessing and investigating the ground conditions and as well the rock formations in order to find the most suitable solution according to the project requirements, and not only this, as well according to the necessities of each different region where those projects have been developed. Engineering geologists, by analyzing the geomechanical properties and as well the physical properties and geochemistry, can ensure the long-term security and safety of those storage sites. So allow me to introduce you a little bit more about the salt caverns. Salt caverns are man-made underground holes created by a process called solution mining, which consists of injecting water in the rock salt formation and dissolving this salt and then washing out this salt to create cavities, underground cavities, to be used to store gas. The depths at which we can find these different, the salt caverns ranges from 200 to 2,000 meters, and salt caverns have been already traditionally used to store natural gas and hydrocarbon products. Although in the last years they've been appointed as well as a very good solution for hydrogen storage, CO2 storage, and as well energy storage in the form of compressed air. Underground gas storage is as well a strategic option to meet fluctuations demands in the electricity grid. So some of the benefits of using salt caverns and underground hydrogen storage is that they offer higher energy density with reduced environmental impacts and increased safety. I'm saying increased safety because this gas is going to be stored several meters below the ground. And salt caverns can also offer lower specific construction cost and a smaller surface footprint, allowing to leave the surface completely free to install other kind of facilities or even to construct roads. And finally, the combination of big volumes and large ranges of operation pressures allows a typical salt cavern to store up to 60 times the normal volume, the traditional volume of a traditional gas tank. So we can see a lot of different ranges of operating, pressures to operate salt caverns depending on the storage activity that we are going to be developing. We can have since very small, from very small ranges of pressures going from 2 megapascals to 8 megapascals to larger ranges of pressures from 0 to up to 30 megapascals. So salt caverns are very good either to allocate peak loads or short-term storage, but as well they are very good to allocate long-term and seasonal storage. So depending on if we are going to be using the salt caverns to store compressed air, we're going to have more daily or weekly cycles. This is going to compromise or imply lower ranges of temperatures. And if we are using the salt caverns to store natural gas of hydrogen, we are going to need larger ranges of pressures for larger periods of time. So some of the challenges of using salt caverns is that salt rock tends to creep. Creep deformation can lead to the closure of salt caverns, and therefore we can lose the volume, the available volume to store gas. Another challenges that we face when working with salt caverns is due to the heterogeneity of the rock salt. Rock soil can present secondary mineralogies, and those secondary mineralogies can have a completely different rheological behavior under the same stress conditions than halite. Actually, here in this plot, what I wanted to show you was a stress-strain plot where you can see the ductile behavior of halite compared to other more brittle behavior of gypsum and glauberite. And finally, on top of those challenges, we have the challenges of having a fluctuation of pressures and temperatures as a result of the operation activity in soil caverns. So engineering geologists need to consider a lot of different parameters when designing and during the construction of the soil caverns. The most important thing is to do a very good characterization of the geological formation. We need to know the thickness and the extension of this geological formation, this rock soil formation, and then a very important thing is to know what other geological materials and secondary mineralogies we can find interlying the rock soil formation that could imply a bigger development of fractures and then compromising the tightness of the soil cavern. So taking all these parameters into consideration, then we'll have the size, the final size of our soil caverns, the available volume from our soil caverns, and as well the separation or the maximum number of soil caverns that this geological formation can allocate. And for this reason, it's very important, a very good characterization of the rock soil formation, because the future safety and mechanical integrity of this soil cavern, it's going to be very influenced by those parameters. So now allow me to show you some of the results from my research. During my PhD thesis, I got to test some samples from Bulby Mine. This is the Zechstein group, the Permian Zechstein group in the east coast of England. And my PhD was about assessing the impacts of second phase content, such as polyhalite or anhydrite, on the rheological behavior under cyclic conditions applied to underground gas storage. In this plot, you can see I've been putting in order from top to the bottom different samples with higher purity halite on top and lower purity halite on the bottom, and therefore with an increased content of second phase content such as anhydrite and polyhalite. And what I could observe after applying mechanical conditions, cyclic mechanical conditions between 4.5 and 7.5 at a loading rate of 0.5 kilonewtons per second for a maximum of 48 hours is that the samples with a higher content in anhydrite and polyhalite were recording higher plastic deformation with more brittle deformation and therefore the development of wider networks of fractures. And this was traduced in an increase of strain values. So I could conclude that an increase in second phase content can act as a strength weakening agent. Then I decided to do further analysis of my data, and I decided to calculate the elastic recovery per cycle. And here on the right, you can see a schematic picture to let you know what I mean by elastic recovery. So what I wanted to record was the strain recovery every time I was unloading my sample. So I was applying a load, then unloading within a cycle, and when I was unloading the sample, I could observe that there was a slightly recovery in the strain. In the other plot on the left, you can see that the samples with a lower composition, with a lower content in halite, lower purity in halite, were the samples with a higher elastic recovery per cycle. And the samples with a higher content in halite were showing less recovery, elastic recovery. I could observe that these new fractures as results of the cyclic damage were also acting as a sliding pathway for the recovery of the sample during the unloading period during the test. Then I could see as well that the samples with a higher content in halite and as well polyhalite were showing a higher increase of this elastic recovery property due to the cyclic damage accumulation. After performing my test, I performed a structural analysis by using scanning electron microscopy and as well transmitted light microscopy. And the main features I could observe after doing the cyclic mechanical loading test is that major fractures and porosity were linked to the presence of secondary mineralogies or second phase contents in my samples. Here on top right, you can see the fractures I could see, and they were always following the pathway, the same pathway and locations where the second phase contents could be observed in the microscope. Then I could observe as well as a result of the cyclic mechanical loading, I could observe boundary openings between grains of halite, grain boundary sliding and rotation, and as well mineral rotation with microporosity generation around the crystals of anhydrite. So after finishing my PhD, as I told you before, I got the opportunity to join Jacobs. And at Jacobs, I've been able to put into real problems in industry all the knowledge I got to learn back to the university. And I wanted to show you this case study. I got to work in this case study about technical due diligence of salt caverns for hydrogen storage in Utah. And this project was aiming to replace a coal-fired generation plant with combined cycle gas turbines able to burn carbon-free green hydrogen. And this hydrogen was meant to be stored in salt caverns. So I got the chance with a team to review all the different available geological data and geophysical data in order to see if the EPC contracts, the engineering, procurement, and construction contracts, were in line with the geomechanical results. So our interest was to make sure that the injection and withdrawal rates and the pressure, the operation pressures that they had established to operate the salt caverns were in line with the recommendations from the geomechanical reports. After this analysis, we were able as well to assess the geological data and to assess to make sure that the number of salt caverns that they were willing to build was in line with the main recommendations from the geologist. So, as conclusions, I would say it is of great importance that the scientific and technical community keep working with international governments and organizations to find solutions to face the climate change and future challenges ahead. Engineering, geology, and geoscience play an important role to deploy the necessary infrastructure to meet net zero targets from the governments, and both at international and national level. And engineer geologists are very important in order to do good characterization of the underground and provide with the best solution according to the necessities of each different region. Underground energy storage might play, and I think it will play, an important role in the energy transition in order to meet demand fluctuations in the electricity grid, but as well to ensure the energy safety for future generations. And finally, good characterization of the geological materials and rock parameters is key to ensure the long-term safety of salt caverns. And it's very important to take into consideration the impact of the second phase contents, because it could be putting in risk the tightness of the salt cavern. Thank you very much for your attention.